Hello, good evening. Hello. Welcome to today's session. We'll wait for a couple of minutes more to allow for more joins. Okay, so good evening. Welcome to the sixth week of problem solving for this course, Availability and Management of Groundwater Resources. Today we will be discussing some sample problems related to the sixth week's lecture materials that involves topics covered on law of groundwater movement, Darcy's law and applications. So we'll be doing some sample problems that will help you deal with the assignment problems that has been allotted to you for this week. Along with that, we'll be discussing about the assignment problems from the fifth week to current assignment problems. So I think it's about time we will go to the question discussion. Questions will be displayed. You can put in the answers in the chat box if you know the answer, and then we'll move on to the solution. So the first question is, the law of flow of water through the soil was first studied by, was it studied by A. Taylor, Darcy, Jordan, or Lambda? So we have all seen about the Darcy's law. So law of flow of water through soil was first studied by this person named Darcy, and he developed this equation that is describing the rate of flow of water through an aquifer or a soil material as a function of the hydraulic conductivity and hydraulic gradient, and as well as the cross-sectional area. So the answer for this question is option B. It's Darcy. Second question, the coefficient of permeability or simple permeability is expressed in terms of what unit? Is it in centimeter per second, meter per day, feet per day, or all of the mentioned units? So the correct answer is option D, all of the mentioned units. So we know that hydraulic conductivity, coefficient of permeability or permeability is also called as hydraulic conductivity, and it is defined as the velocity of flow of water through the soil at unit hydraulic head. Now, how does hydraulic conductivity get the unit of velocity is in this way. So we know that hydraulic conductivity, the product of hydraulic conductivity and hydraulic gradient gives us the velocity of water that is flowing through the soil media. Now at unit hydraulic gradient, what happens is this value becomes 1. So when this value becomes 1, V will be equal to K. That is, the velocity of flow water will be equal to its hydraulic conductivity at unit hydraulic gradient. So since the unit of velocity is in terms of centimeter per second or meter per second or meter per day, we can say the unit for K is also in terms of the units of the velocity. So this is how it is getting the units of velocity. So basically, permeability is defined as or is representing the property which is which is describing how easily the soil material can transmit water or flow through it, and can also be defined as what the velocity of water that is flowing through the soil when the hydraulic gradient is at unit hydraulic gradient. So that time velocity will be equal to the hydraulic conductivity, and it gets a unit of velocity, which is in this way. Next question. The Darcy's law is valid for only what kind of flow? Is it valid for only laminar flow, turbulent flow, hydraulic flow, or all of the mentioned? Okay. So Darcy's law, as we know, is describing the rate of flow of water through the soil media, which is a product of the hydraulic conductivity and hydraulic gradient. Now, there are some assumptions based on which this law was developed. So, Darcy's law is only valid for laminar flow. Laminar flow is nothing but a uh, smooth flow through the material, and according to Darcy, the validity of this Darcy's law is valid only for laminar flow. In soils, there are both kinds of flow. There can be laminar flow as well as turbulent flow, but Darcy's law is only valid for the soil materials through which laminar flow happens. And here you can see the fine-grained sediments, fine-grained sand materials, the flow will be laminar. But when it comes to coarse-grained sediments and there's huge pore spaces in between them, the flow that is happening tends to be a little turbulent. So then we cannot use the Darcy's law to compute the velocity or discharge rate of water flowing through it for turbulent flow. And as you can see here, it is also mentioned that Darcy's law is only valid for slow viscous flow. And most of the groundwater falls under this category where the Reynolds number is very small for laminar flow. So these are the assumptions of Darcy's law. The soil has to be saturated. The flow occurring should be laminar. The flow occurring should also be continuous and steady, and the total cross-sectional area of the soil is considered for computing the velocity according to Darcy's law. So these are four important assumptions that Darcy has made while for the application of this Darcy's equation. That is, the soil should be saturated in order for this Darcy's law to be valid. In other cases, the flow has to be laminar in the soil material, steady flow, that is, it is not changing with time, and cross-sectional area is also considered for the computation of the velocity. So, Darcy's law is only valid for option A, laminar flow. So, correct answer is option A. Question 4. The coefficient of permeability is equal to the velocity of flow. When does this happen? When does the coefficient of permeability become equal to the velocity of flow? When is it when hydraulic gradient is 1, hydraulic gradient is less than 1? Is it when hydraulic gradient is greater than 1? Or is it when hydraulic gradient is 0? So the correct answer is option A. So we had earlier discussed about how the coefficient of permeability obtained its units. So the hydraulic conductivity can also be defined as the velocity of flow of water through the soil when the hydraulic gradient is 1. Hydraulic gradient is nothing but this term I. So when I is equal to 1, V becomes equal to K, and hence P becomes equal to the hydraulic conductivity. So coefficient of permeability is equal to the velocity of flow when the hydraulic gradient is equal to 1. Option A is the correct answer. Moving on to the next question. Question 5. This is a numerical. So if the travel distance of tracer between two wells is 15 meters and the required time for tracer to travel between the two wells is 3 hours, what is the actual velocity of the tracer? So here they are talking about some tracer. Tracer is nothing but it's a chemical compound that will help in obtaining the path of the water flow between 2 points. So here they're saying that distance between the two wells is 15 meters. That is, this is a distance that the tracer has to travel, and the time taken by this tracer to travel between these two wells is 3 hours. So we have to find the velocity of the tracer. It's a simple arithmetical problem. Okay. So there are two terms that we can take away from this question. One is the actual velocity of tracer, and the other is the traveling time of water. So traveling time of water is given by how much distance water travels, or the length uh, of, uh, the length through which the water travels when it comes to groundwater flow, divided by the velocity of groundwater flow into the porosity is gives us the traveling time of water. When it comes to groundwater flow, the traveling time of water is the distance traveled by this groundwater flow or groundwater divided by the velocity of the water into the porosity. Another term that is coming here is the actual velocity of tracer. So tracer is actually used for various purposes like understanding if there is any contamination in groundwater or the path of groundwater, and so on. It gets illuminated certain chemical compounds. So this will help us in understanding flow path and what path this tracer is actually taking. So in order to obtain the actual velocity of the tracer, you have to just divide the distance of the tracer divided by the time, the distance between the 2 points and the time taken for the tracer to travel, which will give the actual velocity of the tracer. Now, this is what has been asked in the question. So here they have given that the distance between the two wells is 15 meter. R is depicting the travel distance of tracer between the two wells, which is 15 meter. T is depicting the time 3. So 15 divided by 3 will give us 5 meter per hour. So it's a very simple arithmetic. It is just the equation for obtaining the velocity distance by time. But what you need to be careful about is when they say, when they ask you to compute the traveling time of water, which is given by the ratio of the distance taken traveled by the groundwater divided by its velocity into the porosity of the aquifer material is also considered while computing the traveling time of water. So that was one numerical. Now let's move on to the next question. Which of the following factors affects the permeability of soil? Out of the following option, which one affects the permeability of soil? Does grain size affect it? Does specific surface area of particles affect it? Does void ratio of the soil affects, or does all of it affect the permeability of soil? Okay, so let's go to the solution. So the various factors that are affecting permeability can be known through this equation or this representation. So here K, the coefficient of permeability is dependent on this factor C, D square, which is the effective size of the formation material, effective size of the particles that is forming the aquifer. It is dependent on the unit weight of water. It is dependent on the viscosity of water, and it is also dependent on the void ratio. Now, here there's a constant C. The constant C is depicting various features like the grain size distribution, the soil texture, the structure of the soil, porosity, the shape and arrangement of the pores, the property of the fluid that is passing, and the if there are any gas or air that is trapped in the soil, then all these are represented by this constant C. So it is dependent on the effective size, that is the size of the grain particles of the material, aquifer material, unit weight of water, which is actually the properties of the fluid, and as well as the properties of the pore spaces. So here, all of the mentioned options are factors that are impacting the permeability soil. The grain size, which is given by the dm square, specific surface area of particles, the soil texture and soil material is also impacting. Void ratio, which is also there in the equation. Next question. What is the mathematical representation of Reynolds number is given in what form? Is it Reynolds number is it equal to the product of inertial force and viscous force, or is it the sum of inertia and viscous force? Is it the difference between inertia and viscous force, or is it inertial force divided by the viscous force? Let's move on to the answer. So Reynolds number, it's a dimensional quantity that is describing what kind of flow pattern is existing in a what it is describing what is the flow, that what type of flow is happening. So when we consider the flow that is occurring through the aquifer, what kind of flow is occurring through it? Is it a laminar flow or is it a turbulent flow? The requirement of this detail is necessary so that we can apply the Darcy's law. We learned that Darcy's law is valid only for laminar flow. So how do we know if that flow occurring is a laminar or a turbulent flow? This we can find out using the Reynolds number. Now, Reynolds number is given as inertia force by viscous force, and it can also be represented in this form, which is density into velocity into the size of the particle, aquifer material, divided by the dynamic viscosity of water. So Reynolds number can be found out using this equation. In general, it is the inertial force divided by the viscous force, which is the question that was asked. What is the mathematical representation? The option D is the answer for it, is inertial force divided by the viscous force. Moving on to the next question. Which of the following statement is true when it comes to the relation between discharge velocity and seepage velocity? Is seepage velocity always smaller than discharge velocity? Or is seepage velocity, will seepage velocity can never be smaller than discharge velocity? Or is seepage velocity equal to discharge velocity? Or is there no relation between them? Okay, so we move on to the answer. So here you can see we learned about the discharge velocity. Discharge velocity is the velocity with which water is flowing through the aquifer medium, and it is given by the Darcy's law. Now there's another quantity called the seepage velocity, which is nothing but the water flowing, the velocity of water that is flowing through the pore spaces is what is called as a seepage velocity. So obviously, seepage velocity will be always greater than discharge velocity. Why? Because we know that velocity is equal to the velocity is equal to discharge by area. When we calculate the discharge Darcy's velocity or the discharge velocity of water that is flowing through the entire aquifer medium, we are taking into consideration the entire cross-sectional area of the aquifer material. And when we compute the seepage velocity, that is velocity of water that is going through one pore space or one path, we are only considering the area of that pore or area of that network of pores in order to compute the seepage velocity. So definitely seepage, since the cross-sectional area is smaller, velocity will be greater. In the case of discharge velocity, the cross-sectional area is larger. So definitely the velocity will be lesser than that of seepage velocity. So seepage velocity can never be smaller than discharge velocity is the correct option for this answer. And the relation between seepage velocity and discharge velocity is seepage velocity is, you can see here, this is giving the seepage velocity. So K into delta H by delta L will give us the discharge velocity. So discharge velocity by N will give you seepage velocity. So that is one, again, another term that we need to be aware of. What is Darcy's velocity and discharge velocity? Discharge velocity is nothing but that velocity of water through the groundwater flow that is taking place given by the Darcy's equation, while seepage velocity is water that is flowing through the pore spaces. Next question, seepage velocity is it inversely proportional to hydraulic gradient? Is the statement true or false? So we just saw what is seepage velocity. It is proportional to the hydraulic head, the difference in the hydraulic head, and inversely proportional to the length of the flow, directly proportional to the K value. So here they have asked if it is inversely proportional to hydraulic gradient, which is not true. It is directly proportional to hydraulic gradient. So this statement is false. So it's option B. Next question. What are the types of water flow in soil? What kind of flows can occur in soil? Turbulent flow, laminar flow, is it linear flow that is occurring? Or none of the mentioned options or all of the mentioned options? So the correct answer is option A. I had mentioned in the initial slides when we were talking about the validity of Darcy's law. Darcy's law is valid only for laminar flow, but irrespective of that, laminar as well as turbulent flow can occur through a soil medium. In case of coarse grain soils, when pore spaces are bigger, there is erratic and chaotic flow that can happen through the soil media, and that flow is called turbulent. That flow is turbulent. So turbulent as well as laminar flow can occur to the soil medium. Okay, moving on to the next question. What is the coefficient of permeability of fine sand? Is it one and greater than one? 1 10 to the power minus 6 and smaller than that, between 10 to the power minus 2 and 5 into 10 to the power minus 3, or between 5 into 10 to the power minus 2 and 1 into 10 to the power minus 3. So let's check the answer. So here it is option B. So these are the permeability, coefficient of permeability in centimeter per second for various soil types. So gravel has the highest hydraulic conductivity, which is 1 to 100 centimeter per second. Coarse sand, again 1 to 0.01 or 0.01 to 1. Fine sand, it is 0.01 to 0.001. Silty sand, it is 0.001 to zero point 0.1 into 10 to the power minus 5. And clay has less than 1 into 10 to the power 6. So the question asked about is about fine sand. Fine sand has a hydraulic coefficient of permeability between 0.01, that is 1 into 10 to the power minus 2 to 1 into 10 to the power minus 3. And the option this option is near to what is the coefficient of permeability of sand. So it's option D, which is the correct answer. Now, next question. What is the energy possessed by virtue of its position or state called as? Is it called pressure energy, elevation energy, dynamic energy, or both A and B? Yeah. So let's get into what all these terms are. So here, pressure energy and elevation energy are forms of potential energy, which is the energy of a body with respect to its position or state. So pressure energy or and elevation energy, they are dependent on the height of the water column. So that is why it is related to the position of state. Elevation energy, uh, yes. So the question, and then the third form of energy is kinetic energy, which is the energy that is possessed by moving water. So energy that is possessed as a result of its position is called the pressure energy, and elevation energy comes under that. And kinetic energy is the energy that is associated with the movement of water. Kinetic energy is also called as the velocity head or dynamic head. So the different forms of the terms used for kinetic energy is dynamic energy, kinetic energy, velocity head, or dynamic head. So the correct answer for this question would be option D, pressure energy and elevation energy. Both of these energy are possessed by virtue of its position. Now here, what is the correct expression provided over here? Here is the terminologies for these symbols. E is the energy per unit weight or the total head of the water. Total energy possessed by water. V is the velocity of the water. G, acceleration due to gravity. T is the pressure at that point. Rho, density. G, acceleration due to gravity. Z is the elevation of the measuring point related to data. So which out of these following expression is the correct expression? Okay. So we see here this term E is equal to V square by 2G plus P by rho G plus Z is what is given over here, and which is the correct answer. So let's see what these terms are. So energy per unit weight or the total energy of water. So where is this required? Suppose we have a confined aquifer and the water available inside the between the confined aquifer is under a particular pressure. The total energy of that water would be the sum of the kinetic energy of water, the pressure energy of water, and the elevation energy of that water. Now, elevation energy is nothing but what will be the height of the reference point to the point which is measured. Pressure energy will be the fluid pressure, that is the energy that is possessed by the fluid at that particular point that is used for measuring. And velocity head or the kinetic energy is the energy that is possessed as a result of the movement of the water. So it is the total sum of all these energy that gives us the total energy possessed by water. V square by 2g is representative of its velocity head. P by rho g is representative of its pressure energy, and Z is representative of the elevation energy. So another name for this elevation energy is gravitational potential energy. As a virtue of its position from the datum, pressure energy as a result of the pressure at a point of measurement, and velocity head is as a result of the velocity or the movement of the water. So the correct option is option A. E is giving us a total head, V square by 2g velocity head, P by rho g pressure head, and Z is elevation head. Now elevation, all these terms are in terms of head, the unit of which will be in meters or centimeters or units of dimensions of length. So this is how we represent pressure in terms of head. Now, which of the following is defining V square by 2g? Is it the energy per unit weight? Is it pressure head, kinetic head, or datum head? Okay. So it's nothing but kinetic head. We learned about energy per unit weight is the total head. Pressure head is the result of the pressure at the pressure exerted by the fluid at that point. Kinetic head is the head as a result of the velocity or the movement of water. Datum head is nothing but the elevation energy. Now again, which of this following is defining the hydraulic head for groundwater flow? So we learned about pressure head, datum head, velocity head. There are different names like gravitational potential head. There is dynamic head. All these terms are there. Now here we are talking about the hydraulic head for groundwater flow. Which out of this following is representing the hydraulic head? Okay. So we know that unlike the flow of water through when the surface water flow and flow through pipes and all, water flow through groundwater is very slow. So we can also consider like it's shown here, it happens at the rate of 1 meter per day. So the kinetic energy is very small when it comes to groundwater. So what we do is we remove the ignore the kinetic energy because the water is flowing at a very minimal velocity, and the flow of water or the energy of water is only represented by the position of the fluid particle at that particular point, which is given by the pressure energy and elevation energy. So after removing the kinetic energy term and rearranging the equation, this sum of the pressure energy and datum head or elevation energy is what gives us the hydraulic head of the water. So groundwater, when we say what is the direction of the flow of water, it will be from a higher hydraulic head to a position of lower hydraulic head. So this is what is called as the hydraulic head. We have seen that hydraulic head divided, the difference in the hydraulic head divided by the length of the flow path is what is giving us the hydraulic gradient dependent, that is on which the velocity of flow is dependent. So this is what hydraulic head is. So hydraulic head is the sum of the pressure head and the datum head. Pressure head is given by P by rho g, datum head is given by Z. So the correct option is option C. Hydraulic head equal to P by rho g plus Z. Now this is a numerical. Here the hydraulic conductivity of a material is given. The K value is given as 30 meter per day. There are two piezometers located. Piezometers are nothing but giving us a pressure of the water at different points. So two piezometers are located at a distance of 500 meter apart from the central line of the valley. The water level in the first piezometer is 1 meter and the water level in the second piezometer is 1.5 meter from the ground surface. What is the velocity of groundwater flow is the question. So if you look at what is given data, here they have given the hydraulic conductivity K. They have given the distance L. They have also given what is the hydraulic head at a point 1 and point 2. They're asking for the velocity of the groundwater flow. How can we find out the velocity? By applying which equation? It's a direct substitution problem. Okay. So the given information is the distance between the two piezometers, L equal to 500 meter. They've given K value 30 meter per day. So the difference of water level between the two piezometers will be 1.5 minus 1 meter, which is 0.5 meter. Now this is giving us the difference in the hydraulic head. This is giving us K value. This is giving us L value. Substituting this in the Darcy's equation, which is V is equal to K into I, where I is equal to delta H by L. Delta H is nothing but the difference between the two levels, H2 minus H1, which is 0.5. So 30 into 0.5 divided by 500. Let's look at all the units. All the units are in terms of meters, so we don't need to convert anything to any other unit. So direct substitution and you get the answer as 0.03 meter per day. So it's option A, which is the correct answer. Okay. Now for the same question, for the same data, they have asked what is the porosity of the aquifer material. If the porosity of the aquifer material is 30%, what will be the traveling time of water from the head of the valley to the point of 15 kilometers downstream? So here they are asking that we found out the velocity of water is 0.03 meter per day. Now, if the porosity is given, what will be the traveling time of water for a distance of 15 kilometers? So we had learned about that equation regarding traveling time, which is nothing but the distance traveled by the water divided by its velocity into porosity. So applying that equation, we will get the answer. Okay, so let's see. Here, like I said, the formula is the traveling time of water is equal to distance traveled by the water or the length of the path divided by the velocity. We know the velocity is calculated as 0.03 meter per day. N is the porosity of the aquifer material. So since it is in percentage, let's convert it to value which is 0.3. So multiplying, dividing the distance in kilometers. We have all the units in meters. So we'll divide 50,000 divided by 0.03 is the velocity of water into the porosity. Porosity is point 3. Since the value here, we require the value in years and not in days. And since this value is in year, we multiply this by 1 by 365 to convert days into years. And we get that the traveling time of water is 411 years. So just explaining this, so you can see that how slowly water travels for a distance of 15 kilometers. It is going to take with this velocity 0.03 meters per day. It is going to take around 411 years for water to travel a 15-kilometer distance. So that's slow. How is water movement in the groundwater level? Moving on, let's discuss some questions from the fifth assignment, which was submitted on the 30th or 31st of August. So the first question was, again, something we discussed. Permeability is affected by all of the following factors except grain size distribution, soil texture, soil structure, and specific gravity of water. So we had checked out on what are the factors impacting permeability of the material. So the grain size distribution is again one factor that is coming under the C constant. Soil texture, soil structure, all of it impact the permeability. Apart from that, the void ratio as well as the fluid property, the unit weight of the water, the viscosity of the water, and the grain, the effective size of the grain particle is also impacting permeability. Now, what is that which is not impacting? It is specific gravity of water. Specific gravity of water is nothing but it is equal to 1, and it is not impacting permeability. It is a unit weight of water that is impacting permeability. Specific gravity is nothing but the density of a material to the density of water is what gives us a specific gravity of a material. Since it is water we are talking about, specific gravity of water is 1, and it is not a factor that is involved in affecting permeability. So option D is the correct option. The specific gravity of water which is not affecting Do not get confused of it with the unit weight of water. Now, another question was, which of the following rock formation has the highest porosity? We can see here sandstone and limestone are two sedimentary rocks, and granite is an igneous rock. Marble is a metamorphic rock, and we know that sandstone, the sedimentary rocks are more porous when compared to granite, igneous and metamorphic rock, and form good aquifer materials. But since here two options are there, out of these two options, which one has the highest porosity? It is sandstone. Last week we had checked out a question which asked about the permeability, which is more permeable. Is it sandstone aquifers or is it fractured limestone and basalt? And the answer was fractured limestone. That is because water flows more easily through the fractures rather than the pores. So that is why fractured limestones form better aquifer when comparison to sandstone aquifers, although the porosity of the material is higher for sandstone. Another question was the permeability. What does permeability refer to? Is it the volume of the water that is released from groundwater storage per unit surface area of aquifer? Is the density of the soil or rock material, the solids and the voids after drying? Is it the ability of a rock or soil to transmit water through its void spaces, or is it the measure of the void spaces that is filled by recoverable oil or grass? Yes. So the option C is the correct answer. We know permeability is describing the ease with which water will flow through the aquifer medium. So this option C, the ability of a rock or a soil to transmit water through its void spaces. The volume of the volume of water released from groundwater storage per unit surface area of the aquifer per hydraulic head can be described as a specific gravity. Okay, here that's not a correct option for specific. Sorry, it's not specific gravity, specific yield. Now, intrinsic or specific permeability is represented with which of the following equation? So this is something that we haven't looked into. The option A is the correct answer. Intrinsic permeability is represented by the product of a constant C and D square, which is giving us the effective size of the particle of the aquifer. So intrinsic or specific permeability, it is characterizing the ability of the porous medium to transmit fluid, and it is actually a property of that aquifer medium or the soil medium. Now, what is the difference between intrinsic permeability and coefficient of permeability? Intrinsic permeability is a property of the medium, whereas coefficient of permeability is depicting the properties of the medium as well as the property of the fluid that is passing through it. So coefficient of permeability also depends on the property of the fluid passing through it, whereas intrinsic permeability is only describing the material property, is only dependent on the material properties through which water is flowing. So the intrinsic permeability is given by a small k, which is equal to CD square. CD is a constant which is representing the properties of the material, soil material, aquifer material, or whatever porous material. What is the size of the, what is the grain size distribution, the packing, what is the soil structure, how is the material packed, the orientation of the material. All of this is being provided by the constancy, and D is the effective size of the material of the aquifer. Now, K is usually expressed, small k, that is intrinsic permeability, is expressed in terms of centimeter square. So, in order to make it more practical unit, Darcy provided a unit called Darcy for K, which is equal to 0.987 into 10 to the power minus 8 centimeter square. Now, how is intrinsic permeability related to coefficient of permeability? It is the product of coefficient of permeability is the product of intrinsic permeability into the unit weight of water by viscosity of water. This is depicting the properties of the fluid, and this is depicting the properties of the material. Nature also has to be taken care that while determining the permeability, water has to be at a standard temperature of 20 or 27 degrees, and they are expressed in terms of centimeter per second and meter per second. So that's about intrinsic permeability. A soil sample with less amount of space between the particles will have a low permeability, porosity, high permeability, high capillarity, or low infiltration rate. A pretty direct question. When the pore spaces is less, it will have low porosity. Again, a numerical. Here an aquifer thickness is given, hydraulic conductivity is given. You're asked to find the transmissivity. Okay. So again, this is a matter of knowing the equation. We know transmissivity is equal to the hydraulic conductivity into thickness of the aquifer. So here thickness has been given as 668 meter. Hydraulic conductivity is 1.5 into 10 to the power minus 6 meter per second. Be careful of the unit, and we need the transmissivity in terms of meter square per day. So multiplying these two values, 668 into 1.5 into 10 to the power minus 6, we get this answer in terms of meter square per second. After converting it to meter square per day, we will get 86.57, which is nothing but the option A. So option A is the correct answer. Once again, transmittivity is the product of the hydraulic conductivity and the thickness of the aquifer. Hydraulic conductivity is given, thickness is given, find out the transmissivity, convert it to the unit that is required in the solution, and we get the answer. And here it is option A, which is the right answer. Another problem, a soil sample has a volume of voids of 50 centimeter cube and the total volume of the core of 200 centimeter cube. What will be the porosity of the sample? So here soil sample, volume of voids is given, total volume is given, porosity, it is nothing but ratio of the volume of voids to the total volume. So direct substitution, 50 divided by 200, you will get 0.25, and it has to be expressed in percentage. So you multiply it with 100 and get 25%, which is option C. Once again, volume of the voids divided by the total volume of the sample is what is porosity. So for dividing 50 by 200, we will, and multiplying it with 100, we will get a percentage. Porosity in terms of percentage. Another question, an unconfined aquifer has a specific retention of 0.15, porosity of 0.35. What is the specific yield? This is also a very direct substitution question. Once you know the formula relating porosity, specific yield, and specific retention. Moving on, we know the relation between specific yield, specific retention, and porosity is nothing but sum of the specific yield and specific retention is equal to porosity. So here we've been given for a specific retention and porosity. So n minus the specific retention will give the specific yield. N is 0.35, specific retention is 0.15. So 0.35 minus 0.15 will be 0.2. So specific yield is 0.2. In terms of percentage, it will be 20%. So option B will be the correct answer. Once again, specific the sum of specific yield plus specific retention is equal to porosity. So since porosity and specific retention is given, we will minus n minus SR, which is 0.35 minus 0.15, gives us the specific yield, which is option B. The dimension of transmissivity is which out of the following? Okay. So we know that transmissivity is depicted in terms of centimeter square per second. So if you see here, the unit here m, the dimension m relates to mass, L relates to the units for length, and T relates to units for time. So it is definitely not having any term that is depicting mass of it. So here this option, the dimension of m is 0, L is to the power 2, and T is to the power minus 1, which is giving us the correct answer. Centimeter square per a second, so T to the power minus 1. So the correct answer for this question would be option B. So that's it for today's discussion. If there's any doubt regarding the questions we have discussed or regarding the assignment questions, please do ask. Otherwise, we'll be ending, I mean, it will be the end of the session. End of the question discussion. I'll be around for some more time. So if there's any doubt, please do let me know. Thank you. Okay, so I'll be ending the session now. Thank you for attending the session and see you next week with the question discussion on this week 7 lecture materials. Have a good day and a good weekend. Bye.